It began on an ordinary night, a data dump from observatories around the world, arrays of numbers and timestamps that most people would never see. Somewhere in the Harvard Astrophysics Center, a small team noticed a line in that feed that did not conform. Professor Loeb's initial reaction was professional skepticism. He had seen instrument glitches, miscalibrations, and cosmic rays that masqueraded as anomalies. But the numbers were persistent. They repeated across independent data sets. They pointed to a single, alarming conclusion. 3I Atlas was not behaving like any comet or small body humanity had catalogued. On November 9th, 2 images arrived that made the quiet of data rooms dissolve into stunned silence. One came from the James Webb Space Telescope. The other was released by the Virtual Telescope Project. Both instruments, one orbiting in the cold, infrared reach of space, the other a coordinated network of ground-based optics, captured the interstellar object in a way no one expected. Instead of a diffuse nucleus surrounded by a growing coma and a ghostly tail stretching away from the sun, both showed a compact, brilliant point of light, small, sharp-edged, and utterly unchanged from the photos Hubble had taken in July. That unchanged appearance was the challenge. Over the intervening months, solar heating should have stripped billions of tons of volatiles from a body passing so close to the sun. If 3I Atlas had been a conventional comet, a so-called dirty snowball of ice, dust, and rock, it would have bloomed into a sprawling cloud, a halo visible even through small telescopes, and projected a tail shaped by solar radiation pressure. Instead, the object looked the same. Its magnitude, its color, and even its point-like symmetry offered no hint of the violent mass loss the orbital dynamics suggested it must have undergone. For some researchers, that was an anomaly to file under unexpected but explainable. For others, including Loeb, it was a wake-up call, a statistical and physical objection to the assumption that 3I Atlas was a natural comet at all. The first peculiarity that alerted orbital mission analysts was not its appearance, but its trajectory. During late October, as the object approached perihelion, its closest passage to the Sun, its motion deviated from predictions. NASA's Jet Propulsion Laboratory reported a deflection of roughly 4 arc-seconds. At a distance of 203 million kilometers, that angular offset translated to tens of thousands of kilometers across linear space. It was not random jitter. It was a sustained, measurable departure from where the object should have been. The calculations that converted arc-seconds to kilometers produced a figure mission teams could not ignore. Something was applying force to 3I Atlas in a way that standard models could not reproduce. Outgassing the classical explanation for cometary non-gravitational accelerations was examined and then largely rejected for this case. To generate the thrust required to produce the observed acceleration and sideways drift, a conventional cometary model would demand the expulsion of at least 1/6 of the object's total mass in vaporized material. In practical terms, that equates to, on the order of 5 billion tons of gas vented into space, a luminous, scattering haze that should have been unmistakable. Backyard telescopes, amateur surveys, and professional arrays would have recorded it as a brilliant halo. Yet, sky surveys remained bereft of such a plume. The vacuum around the point of light was empty. No expanding shell of dust, no bright coma, nothing. To make the discrepancy concrete, the Virtual Telescope Project juxtaposed a contemporaneous image of a completely ordinary comet, Comet Lemon, taken under comparable viewing conditions. Lemon behaved predictably: a luminous head, a ghostly tail streaming away from the sun, clear evidence of outgassing shaped by the solar wind. 3I Atlas, in contrast, remained a compact dot, sharp against the stellar backdrop. The visual comparison was damning in its simplicity. One object surrendered its mass and revealed its nature. The other guarded its form and confounded expectations. Witnesses compared the two as one might compare a living, breathing animal to a carved statue. When Loeb and his team conducted the energy budget reconstructions, the scale of the problem deepened. Using conservative estimates that placed 3I Atlas's mass at approximately 33 billion tons, orders of magnitude heavier than the earlier interstellar visitor, Oumuamua, they derived the physical implications of the measured acceleration. Solar radiation pressure was literally too weak, by factors of many, to account for the observed motion. Gravitational perturbations from known planetary bodies were negligible at that distance. Outgassing, mathematically, would have produced a globular, observable emission. But telescopes recorded a stubborn emptiness. The inference followed inexorably. Either some unknown natural mechanism was in play, or an altogether different class of phenomenon was responsible. That altogether different possibility is uncomfortable in scientific discourse because it broaches the artificial. If the observed motion is not the product of passive physical processes, then what remains? At its most provocative, the data could be consistent with active control, some directed force applied to the object from within or to the ensemble of fragments. To many, this reads as a speculative leap. To others, the mathematics demanded a leap. If 3I Atlas accelerated without producing detectable reaction mass, then the source of thrust must lie outside the textbook explanations. The anomalous trajectory was only one thread in the knot. Spectroscopic investigations added texture and another set of contradictions. Webb and ground-based spectrographs examined the light and resolved a chemical composition that looked at first glance peculiar in the context of cometary archetypes. The nickel-to-iron ratios in the spectroscopic lines skewed toward a metallic balance reminiscent of high-temperature alloys used in engineered systems, materials known to human metallurgy as the backbone of turbines and heat-resistant components. In nature, metals coagulate under different regimes, and the resultant ratios are generally messy and variable. 3I Atlas's apparent compositional signature hinted at homogeneity and balance. Further compounding the oddity was the near absence of water, only about 4% by mass, where cometary bodies typically range far higher. The object thus presented a paradox: compositionally dry, spectrally metallic, morphologically unchanged, and dynamically errant. Beyond composition, the color itself turned into a clue that would not be ignored. Observers initially catalogued color shifts across months, subtle changes consistent with changing phase angles and variable outgassing. Then, in late October and into early November, the object's spectrum swung toward a deep electric blue-blue with a spectral intensity implying physical processes capable of producing photons at energies higher than expected for a small, passive, solar-heated body. Blue light corresponds to short wavelengths and, in thermal emission, implies higher effective temperatures. The sun's photosphere, at approximately 5,800 Kelvin, sets a natural comparative scale. For an object like a comet to radiate bluer, then that would mean surface conditions hotter than a star's visible surface, a literal impossibility for a passive aggregation of rock and volatile ices without vaporizing entirely. Yet, instruments reported this blue bias with consistent readings across multiple platforms. In other words, the object was not just reflecting blue light, it appeared to be producing or modulating it. If that were not enough to keep the files open and the teams awake at night, the timing and geometry of 3IA-TLAS's path introduced another discomforting dimension. Its orbit lay nearly in the ecliptic plane within 5 degrees of Earth's orbital path, such that its passage threaded between planetary orbits in a way that some quantified as extraordinarily improbable. The object's perihelion geometry further complicated matters. At the point when it should have presented the best phase for Earth-based observation, it instead transited behind the Sun, temporarily concealed from our primary view. Later, when data were plotted in reverse, analysts observed that the inbound vector correlated with a small swath of the sky that, decades earlier, had returned one of the most famous anomalous radio events in human history, the WOW signal of 1977. Two events, observed nearly 50 years apart, that both trace back to the same general sky coordinates. Coincidence is possible, but as data accretes, denial becomes harder to justify.